Okay, let's just dive right in. Think about any game you've ever played. It has rules, right? A clear set of instructions that everyone agrees on, just so you can actually play the game. Well, what if I told you that all of modern mathematics has its own rulebook? A set of foundational instructions that almost everything is built on. And it's a rulebook that most of us have never even seen.
I mean, that's a huge question, isn't it? We use math every single day, but what's actually holding it all together? What's the bedrock that everything from, say, calculus to computer science is resting on?
Well, the answer is kind of like a hidden operating system. You know, just like the OS on your phone or computer that runs everything in the background without you even noticing. Mathematics has its own fundamental code. It's this engine, humming away quietly, making the entire world of modern math even possible.
In this system, it has a name, ZFC. That stands for the Zermelo-Fraenkel axioms, with the very special and, as we'll see, very controversial axiom of choice. In that last part, well, that's where the real story begins.
So how exactly does ZFC work as this operating system for math? Let's get into it.
Think of it like this. ZFC isn't just one theory out of many, it's more like the common language. It's what lets mathematicians all over the world build on each other's work. It's the shared ground rules that make sure when someone proves a theorem in Tokyo, it means the exact same thing in Toronto. It really is the universal starting line for almost all of modern mathematics.
Okay, so we know it's super important. But what is it really? Let's break down what it's made of.
At its heart, ZFC is what we call an axiomatic system. So imagine those are the absolute, most basic rules of the game, the things you just have to accept as true before you can even start playing. From these few simple starting points, the entire vast, complex universe of mathematics is logically built piece by piece.
And the name itself, ZFC, it tells a story. The Z is for Ernst Zermelo, who first laid out all these rules way back in 1908. The F is for Abraham Fraenkel, who came along and helped polish them up. And then there's the C. This stands for the Axiom of Choice, an idea so powerful and so strange that it nearly tore the entire mathematical world in two.
And this is where our story gets really, really interesting, because the C in ZFC wasn't just another rule. Nope, it was a philosophical bombshell.
You see, when Zermelo first proposed the axiom of choice in 1904, the reaction was immediate and it was fierce. It kicked off what became known in German as the Grundlagenkrise der Mathematik, which literally means the foundational crisis of mathematics. The whole field was in an uproar. The debate got so intense that Zermelo had to formalize his entire system of axioms just to defend this one single controversial idea.
This fight wasn't really just about math. It was this deep, philosophical clash about the nature of truth itself. So on one side, you had the Platonists. They believed math is discovered. They saw mathematical objects as real things, just existing out there in some abstract world, and the axiom of choice was just another tool to find them. But then you had the Constructivists, and they believed math is invented. For them, you couldn't just say something exists unless you could show the exact recipe to build it. And the axiom of choice, which basically says, hey, I know there's a matching sock for every single sock in this infinite pile, but sorry, I can't show you how to pick them out. To them, that was just cheating.
So, after all that drama, why did ZFC, including that controversial axiom, end up winning out? Why does it matter so much to us today?
Well, it turns out this isn't just some abstract philosophical thing. Take this quote. Entire fields like control theory, that's the math behind everything from robotics to economics, they would pretty much evaporate without the axiom of choice. And why is that? Because it's the one rule that guarantees certain vital solutions exist, even if we can't write down the exact instructions to find them. So, ZFC is powerful, it's absolutely essential, but does that mean this rulebook is perfect? Can it answer every single mathematical question you could possibly ask?
Not quite, and this is where things get truly mind-bending. You see, ZFC is strong enough to let us ask these incredibly deep questions, but it can't always give us the answers. The most famous example of this is the continuum hypothesis, which is a question about the nature of infinity. Get this, in the 1960s, mathematicians proved that you can neither prove nor disprove this hypothesis using the rules of ZFC. I mean, just think about that. It means the rulebook itself is incomplete. You could just add a new axiom saying the hypothesis is true, or add one saying it's false, and you'd create two totally different but perfectly consistent versions of mathematics.
So, that naturally leads to another question.
If ZFC has these limits and was so controversial to begin with, are there any other options out there?
And the answer is a definite yes. The search for the perfect mathematical rulebook never really stopped. Today, you've got these ambitious modern projects like Univalent Foundations trying to rebuild math from the ground up on a new base. You even have critiques arguing that maybe we don't even need the most complicated parts of ZFC for practical science. The debate that Zermelo kicked off over a century ago, it's still very much alive.
And that's what's so cool about this. The story of ZFC forces us to face the biggest question of all about math. Are we discovering these timeless, eternal truths about the universe, like the Platonists thought? Or are we just inventing a really magnificent game, defined by whatever rules we choose to play by, like the Constructivists argued? That hidden operating system we all rely on, it doesn't give us the answer. Instead, it just shows us that the question itself is what really matters.